These are the numbers that cosmologists cannot make agree with each other, no matter how many times they check the math. And the disagreement is the reason nobody can tell you exactly how fast the universe you live in is actually growing. This is the story of what happened when two completely different ways of measuring the universe's expansion gave two different answers, and neither side has been able to prove the other wrong. If you're watching this late at night, get comfortable, because we're going to walk through more than a century of observation, argument, and revision to get to where cosmology stands today. Before we get into it, if you enjoy this kind of deep, slow dive into the biggest questions in science, consider subscribing and drop a comment telling me where in the world you're watching from and what you're doing right now, whether that's winding down for the night, driving, or just curious. I read every one of them, and I genuinely love seeing who's out there. Now, let's get into it. Everything in this story starts with a simple observation that turned out to be anything but simple. Space is stretching. Not the galaxies moving through space like ships crossing an ocean, but the space between them growing, carrying the galaxies along for the ride whether they like it or not. And the strange part isn't that this stretching happens. Scientists agree on that completely. The strange part is that when two independent groups of researchers try to measure exactly how fast that stretching is happening, using two different methods, they get two different numbers, and the gap between those numbers has only grown wider and harder to explain the more precisely anyone measures it. Let's spend a moment on what it actually means for space itself to stretch, because it's a stranger idea than it first sounds, and almost everything else in this video depends on understanding it properly. When astronomers say a galaxy is receding from us, they don't mean it's firing rockets and flying away through a fixed, unmoving backdrop of space, the way a plane flies away from an airport through unmoving air. They mean the fabric of space between here and that galaxy is itself growing, continuously, everywhere, all the time. Picture a loaf of raisin bread rising in an oven. Every raisin sees every other raisin moving away from it, not because any individual raisin is crawling through the dough, but because the dough itself, the medium connecting all of them, is expanding in every direction at once. The farther apart two raisins start out, the faster the dough expanding between them pushes them apart, purely as a consequence of geometry, not motion. That's the picture cosmologists have in mind when they talk about cosmic expansion, and it's why the relationship discovered in the late 1920s, the farther away a galaxy is, the faster it appears to recede, isn't some strange coincidence. It's the direct mathematical consequence of a stretching fabric of space carrying galaxies along with it. There's a second image that captures a slightly different piece of the same idea, one you may already have encountered if you've ever taken an introductory astronomy class. Picture the surface of a balloon with small dots drawn on it, representing galaxies, and imagine slowly inflating that balloon. Every dot moves farther away from every other dot as the balloon expands, but critically, none of the dots are actually sliding around on the rubber surface itself. It's the surface itself stretching underneath them that carries them apart. This image is useful specifically because it emphasizes a detail that matters enormously for understanding the observable universe later in this video. There's no special center to the expansion, no single dot on the balloon's surface that all the others are rushing away from. Every single dot sees every other dot receding, and from the point of view of any individual dot, it would look exactly as though it were sitting at the very center of the expansion, even though there's no true center anywhere on that surface at all. The same is true of the real universe. Every galaxy, including our own, would observe every other galaxy receding from it in more or less the same pattern Hubble described, which is exactly what you'd expect from a genuinely uniform stretching of space itself, rather than some special explosion outward from a single, identifiable point that we happen to be sitting at the center of. It's worth taking a moment here, roughly halfway through this story, to notice just how much groundwork has already had to be laid before anyone could even ask the question this video is built around: how fast the universe is expanding. Astronomers first had to establish that spiral nebulae like Andromeda were separate galaxies entirely, rather than clouds within our own Milky Way. They had to develop a reliable way of measuring distances to those galaxies in the first place, which took Henrietta Leavitt's patient cataloging of variable stars. They had to gather redshift measurements, showing those galaxies were moving, which took Vesto Slipher's decade of painstaking spectroscopy in Arizona. And they had to have a theoretical framework, general relativity, capable of predicting that the universe could expand at all, which took Einstein, and then Friedman, de Sitter, and Lemaitre, pushing past Einstein's own reluctance to accept where his equations were pointing. Only once all of those pieces were in place could Hubble, in 1929, finally put distance and velocity on the same graph and reveal the relationship that gives this entire field its name. Keep that layered structure in mind as we move forward, because it's exactly the same layering, one discovery resting on the shoulders of an earlier one, that eventually leads to the still unresolved puzzles making up the second half of this story. Before going further, it's worth pinning down 2 units of measurement that are going to come up constantly for the rest of this video, because the numbers involved are so large that it's easy to lose track of what they actually represent. A light year is simply the distance light travels in 1 year, moving at roughly 300,000 kilometers every second, which works out to a distance of about 9.46 trillion kilometers, or about 5.88 trillion miles. It's a unit of distance, not time, even though the word year sits right there in the middle of it. The other unit that shows up throughout modern cosmology, especially anywhere you see the phrase kilometers per second per megaparsec, is the megaparsec, a unit equal to roughly 3.26 million light-years, used because it keeps the numbers involved in galactic and cosmic distances from becoming even more unwieldy than they already are. When a scientist says the Hubble constant is 70 kilometers per second per megaparsec, they mean that for every 3.26 million light-years of distance separating us from some far-off galaxy, that galaxy appears to be receding from us an additional 70 kilometers per second faster. Double the distance, and, roughly speaking, you double the apparent recession speed, which is exactly the linear relationship Lemaitre worked out on paper in 1927, and Hubble confirmed with data in 1929. This distinction matters because it changes what we mean by the light we receive from distant galaxies. When light leaves a star billions of years ago and eventually reaches our telescopes, it has been traveling the entire time through space that kept stretching underneath it, like a runner sprinting across a rubber sheet that keeps getting pulled longer behind them. That stretching lengthens the light's wavelength along the way, shifting it toward the red end of the spectrum, a phenomenon called cosmological redshift. The more the universe has expanded during the time a particular beam of light spent traveling toward us, the more that light has been redshifted by the time it arrives. Measure that redshift precisely, and you're effectively measuring how much the universe has grown since that light began its journey. This is the tool that made essentially everything in this story possible, from the first evidence of cosmic expansion in the 1920s, all the way through the most precise satellite measurements being published today. Long before anyone had assembled these pieces into a coherent theory, one patient observer had already collected the raw data that would eventually make the whole picture possible. In September of 1912, an astronomer named Vesto Slipher, working at the Lowell Observatory in Flagstaff, Arizona, pointed the observatory's 24-inch telescope at the Andromeda Nebula and began an exposure that would run for hours across several nights. Slipher had spent years improving the observatory's spectrograph, specifically so it could capture usable spectra from objects as faint as these hazy, cloud-like smudges astronomers of the era called spiral nebulae, since nobody yet knew whether they were nearby clouds of gas or something else entirely. When Slipher finally measured the spectral lines in his Andromeda plates, he found a shift corresponding to a velocity of about 300 kilometers per second, roughly 30 times faster than any known stellar motion, and moving toward us rather than away, a blue shift rather than a red shift. It was, at the time, the fastest velocity ever measured for any astronomical object, and it immediately suggested that whatever Andromeda actually was, it wasn't behaving like an ordinary nearby object drifting along with the rest of the Milky Way. Slipher kept going. By 1914, he had measured similar velocity shifts in 15 separate spiral nebulae, and when he presented his results at a meeting of the American Astronomical Society that year, the assembled astronomers reportedly gave him a long-standing ovation, a genuinely unusual reaction at a scientific conference, then or now. By 1917, Slipher had pushed his survey to 25 nebulae, and the pattern held. The overwhelming majority, 21 out of 25, showed red shifts rather than blue shifts, meaning they appeared to be receding from us, and several were moving at speeds far higher than anything found among ordinary stars. Slipher had, without fully realizing the cosmological weight of what he'd found, produced the entire observational backbone that both Lemaitre and Hubble would later lean on to establish the velocity side of the velocity-distance relationship. It's a detail that tends to get lost in the standard telling of this story. The redshift measurements underpinning the discovery of cosmic expansion were mostly Slipher's, gathered patiently over the better part of a decade at a small observatory in Arizona, years before anyone had worked out what those numbers actually implied about the shape and fate of the universe. To understand why the gap between competing expansion rate measurements matters so much today, you have to go back to a period before anyone even knew the universe was expanding at all, back to a time when most scientists, including Albert Einstein, assumed the universe was static, fixed, unchanging on the largest scales, the same yesterday, today, and tomorrow. That assumption turned out to be wrong, and the person who first did the math to prove it wasn't the person most textbooks give credit to. In 1917, Einstein applied his newly finished theory of general relativity to the universe as a whole, and the math told him something he didn't want to hear. His own equations implied a universe that couldn't sit still. It had to be either expanding or contracting. Unwilling to accept that, Einstein added a fudge factor to his equations, a term called the cosmological constant, whose entire purpose was to cancel out the expansion and force the math to describe a static universe instead. He would later call this his greatest blunder, once the observational evidence for an expanding universe became impossible to ignore. There's a strange twist buried in that story worth sitting with for a second. The very term Einstein invented, purely to prevent his equations from describing an expanding universe, the cosmological constant, is essentially the same mathematical tool cosmologists use today to describe dark energy, the force actually driving that expansion to accelerate. Einstein tried to use this term to hold the universe still. Nearly a century later, physicists are using a version of that same term to explain why the universe refuses to stop growing faster and faster. He was wrong about what the universe was doing, but the mathematical device he invented to be wrong with turned out to be exactly what was needed to describe what was actually happening, just pointed in the opposite direction from what he intended. That evidence started arriving through the work of a Russian mathematician named Alexander Friedmann, who in 1922 derived what are now called the Friedmann equations directly from Einstein's own field equations, without the artificial fix Einstein had inserted. Friedmann's equations showed that the universe could expand, and they even gave a formula for how fast that expansion should proceed. Friedmann never got to see this idea vindicated. He died in 1925, years before anyone would confirm it with a telescope, a reminder that some of the most important theoretical breakthroughs in this story were made by people who never lived to see them proven correct. Friedmann wasn't the only physicist wrestling with alternatives to Einstein's static universe during this period either. A Dutch astronomer named Willem de Sitter had proposed his own solution to Einstein's equations a few years earlier, one that described an expanding universe of a particular, almost empty kind, essentially devoid of ordinary matter, held together only by the same cosmological constant Einstein had introduced. De Sitter's model was strange and mathematically interesting, but because it assumed a universe with essentially no matter in it, most physicists at the time treated it as a curious edge case rather than a serious description of the actual cosmos we live in. It would take Lemaitre, a few years later, to work out a version of these non-static solutions that included ordinary matter in a physically realistic way and that could be connected directly to actual astronomical observations of galaxy redshifts, rather than remaining a purely mathematical exercise. It's a useful reminder that the idea of a non-static universe wasn't some sudden, singular insight arrived at by one lone genius, but something several different physicists and mathematicians were independently circling from different angles across the 1920s, each contributing a piece before the full picture came together. 5 years after Friedmann's calculation, a Belgian physicist and Catholic priest named Georges Lemaitre independently arrived at the same kind of non-static solution to Einstein's equations, and he took the idea further than Friedmann or de Sitter had. Lemaitre combined his theoretical work with actual astronomical data, redshift measurements that had been collected by an American astronomer named Vesto Slipher years earlier. along with distance estimates from Edwin Hubble's own prior work. Using that combination, Lemaitre calculated a numerical value for what we'd now call the expansion rate of the universe, somewhere between 575 and 670 kilometers per second per megaparsec, depending on how he grouped the data, and concluded that the universe really was expanding. He published this in 1927, and it should have been a landmark moment in the history of science. There's a small, telling anecdote from this exact period that captures just how resistant even the most brilliant physicist alive at the time was to the idea Lemaitre was proposing. Later in 1927, at the 5th Solvay Conference in Brussels, one of the most important gatherings of physicists in the world that year, Lemaitre finally got the chance to speak with Einstein directly about his paper, which a mutual acquaintance had apparently brought to Einstein's attention. According to Lemaitre's own later recollection, Einstein acknowledged that the mathematics in the paper checked out, but dismissed the physical interpretation entirely, telling him, in French, that his calculations were correct, but his physics was abominable. Einstein, still deeply committed to the idea of a static, unchanging universe at that point, simply wasn't willing to accept what his own equations, worked through independently by both Friedmann and now Lemaitre, were telling him. It would take Hubble's observational confirmation 2 years later, in 1929, along with mounting pressure from within the physics community itself, before Einstein came around to accepting an expanding universe as physically real rather than merely a mathematical curiosity, and eventually to disowning the cosmological constant he'd invented specifically to avoid that exact conclusion. Instead, Lemaitre's 1927 paper went almost completely unnoticed by the wider scientific community at the time, for a reason that has nothing to do with the quality of the physics and everything to do with where it was published. Lemaitre wrote his paper in French and placed it in a relatively obscure Belgian journal that most of the scientific world simply never read. The idea sat there, essentially invisible, for 2 years, quietly waiting for the rest of the field to catch up to what one priest working largely alone had already figured out with nothing more than Einstein's published equations and someone else's telescope data. Then, in 1929, Edwin Hubble, working at Mount Wilson Observatory in California, published his own version of the same velocity-distance relationship, using largely the same redshift data that Slipher had originally collected, combined with his own distance measurements based on Cepheid variable stars. Hubble found that the farther away a galaxy was, the faster it appeared to be receding from us, a clean, roughly linear relationship between distance and recession velocity. This became known as Hubble's law, and for nearly a century, it carried only his name. Here's the detail that makes this such a strange footnote in the history of science. Hubble did not credit Slipher for the redshift data underlying his conclusion, and the theoretical framework Lemaitre had already published 2 years earlier was, at the time, essentially invisible to the broader scientific community because of where it had appeared. It would take until 2018, nearly 90 years later, for the record to be formally corrected. That year, the International Astronomical Union held a vote among its members on whether to rename the relationship the Hubble-Lemaitre law, in recognition of Lemaitre's earlier and independent contribution. The vote passed, with 78% in favor, 20% against, and 2% abstaining. Even the correction became a small controversy in its own right, because a Canadian astronomer later revealed a strange twist. When Lemaitre had his own 1927 paper translated into English for wider publication in 1931, he personally left out the specific numerical value he'd calculated for the expansion rate, the same number Hubble would later become famous for measuring independently. Some historians read that omission as remarkably generous, a scientist quietly stepping back so that Hubble's later, more precise observational work could stand on its own. Others see it simply as an odd historical accident. Either way, it muddies any attempt to draw a clean, simple story out of who discovered what and when, and it's worth sitting with that ambiguity, rather than pretending the history is tidier than it actually is. What matters most for the story we're telling here isn't really who deserves the most credit. It's what this early work established as fact. The universe is expanding. The farther away something is, the faster it's moving away from us, and if you run that expansion backward in time, everything we can see must once have been compressed into an extraordinarily small, dense state. Lemaitre took that logical step further than almost anyone else in the late 1920s and early 1930s. In 1931, he proposed that the universe originated from what he called a primeval atom, a single, ultra-dense point from which everything else emerged. That idea, refined over decades by many other physicists, eventually became what we now call the Big Bang theory. The same year, 1931, Hubble and his observational collaborator, Milton Humason, published a joint paper comparing the distances and velocities of remote galaxies, some of them receding from us at speeds as high as 20,000 kilometers per second, and their data confirmed, with far more precision than before, that recession velocity really does scale with distance, exactly as Lemaitre had suggested on theoretical grounds 4 years earlier. Before we move forward in the timeline, it's worth pausing on the tool that made almost all of this observational progress possible in the first place, because the person behind it deserves far more recognition than she's historically received. Every one of these distance measurements, Hubble's, Lemaitre's, all of it, depended on a method for figuring out how far away a star actually is. And that method traces back to a woman named Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 20th century. Leavitt was one of a group of women employed at Harvard as what were then called computers, hired specifically to examine photographic plates and catalogue the positions and brightness of stars, because the observatory's director at the time believed women were, in his words, better suited to this painstaking work and unsuited to operating the telescopes themselves at night in the cold. Leavitt was assigned to study variable stars in the Magellanic Clouds, 2 small satellite galaxies visible from the southern hemisphere, and over years of meticulous, repetitive work, examining plate after plate, she identified 1,777 individual variable stars. Among those, she focused on a particular class called Cepheid variables, stars whose brightness rises and falls in a completely regular, repeating cycle. In 1912, Leavitt published a short paper examining 25 of these Cepheid variables, specifically located within the small Magellanic Cloud. Because all the stars in that cloud sit at roughly the same distance from Earth, any difference in how bright they appeared to be had to reflect a genuine difference in their true, intrinsic brightness, rather than being an illusion caused by some stars simply being closer to us than others. Working through that data, Leavitt discovered something remarkably clean: a straight-line relationship between how bright a Cepheid appeared to be, on average, and how long its pulsation period was. The brighter the star, the longer the interval between one peak in brightness and the next. This is now called the period luminosity relation, or Leavitt's law, and it handed astronomers something they had never had before: a genuine standard candle, an object whose true brightness could be inferred just by timing how long it took to pulse, which meant its distance could then be calculated simply by comparing that known true brightness against how dim it appeared from Earth. The significance of this cannot be overstated, and it's worth taking a moment to really sit with what it unlocked. Before Leavitt's discovery, astronomers had almost no reliable way to measure distances to objects beyond our own cosmic neighborhood. Stellar parallax, the traditional method, works on a fairly simple geometric principle, the same one your own eyes use to judge distance every day. Hold a finger up in front of your face and look at it first with one eye closed, then the other, and you'll notice it appears to shift slightly against the background behind it. The closer the finger is to your face, the bigger that apparent shift, and the farther away it is, the smaller the shift becomes. Stellar parallax works the same way, except instead of your 2 eyes, astronomers use the Earth's own position on opposite sides of its orbit around the Sun, roughly 6 months apart, as the 2 vantage points. And instead of a finger, they're measuring the tiny apparent shift of a relatively nearby star against far more distant background stars. The trouble is that this apparent shift shrinks rapidly with distance, and for stars beyond a certain range, it becomes too small for even the most precise instruments to measure reliably. That technique runs out of usefulness within a relatively small radius around our own solar system, a limitation that would only be pushed back much later, well into the 21st century, by dedicated satellite missions like the European Space Agency's Gaia, capable of measuring parallax shifts precise enough to reach stars scattered much further across our own galaxy. Leavitt's period luminosity relation blew that limitation wide open. Suddenly, any Cepheid variable, anywhere it could be spotted and timed, however far away, could be used to calculate a genuine distance. Using her law, Cepheids remain useful for measuring distances up to roughly 60 million light-years, an almost unthinkable leap beyond what parallax alone could ever achieve. Leavitt's paper, published as a Harvard College Observatory circular, was formally signed by the observatory's director, Edward Pickering, following the convention of the time, though its opening sentence made clear the work had been prepared by, in its own words, Miss Leavitt. That framing was common practice at Harvard in that era, and it quietly obscured, for decades, just how central her individual insight had been to a discovery that would eventually reshape the entire field of cosmology. Leavitt continued working at the observatory, cataloguing thousands of variable stars over her career, more than 2,400 in total, more than half of all those known by 1930, all without ever operating a telescope herself. She died in 1921, at the age of 53, from stomach cancer. 4 years after her death, in 1925, a Swedish mathematician named Gösta Mittag-Leffler moved to nominate her for the Nobel Prize in Physics, apparently unaware that she had already passed away and was therefore no longer eligible. It is one of the quieter tragedies buried inside this entire story. The woman whose insight made it possible to measure the scale of the universe never lived to see Edwin Hubble use her exact method, a decade after her death, to prove that the Andromeda Nebula was an entirely separate galaxy from our own, and never lived to see that same method become the foundation for discovering that the universe itself was expanding. With Leavitt's tool in hand, it's worth pausing on one more episode from this same period, because it shows just how contested the basic shape of the universe still was, even after Slipher had already measured his puzzling redshifts, and even after Leavitt had already handed astronomers a working method for measuring distance. On the evening of April 26, 1920, two astronomers, Harlow Shapley and Heber Curtis, stood up in front of an audience at the Smithsonian's National Museum of Natural History in Washington, D.C., for what came to be remembered as astronomy's great debate. The official topic was billed simply as the scale of the universe, but underneath that polite title sat a genuinely fundamental disagreement. Shapley argued, using his own measurements of globular star clusters and Leavitt's period luminosity relation, that the Milky Way alone was enormous, roughly 300,000 light-years across, and that the spiral nebulae visible in telescopes, including Andromeda, were simply smaller structures contained within our own galaxy. Curtis took the opposite position, arguing for a considerably smaller Milky Way, something closer to 30,000 light-years across, and insisting that the spiral nebulae were entirely separate galaxies in their own right, what earlier philosophers had called island universes, sitting at almost unimaginably vast distances beyond our own. Neither man had decisive proof at the time, though Curtis did bring one clever piece of circumstantial evidence to the stage that turned out, in hindsight, to be pointing in the right direction. He had noticed that a surprising number of novae, sudden stellar outbursts, seemed to be showing up within the Andromeda Nebula specifically, more than could easily be explained if Andromeda were simply an ordinary patch of the Milky Way like any other. Curtis reasoned that if Andromeda were in fact an entire separate galaxy in its own right, comparable in size and stellar population to our own Milky Way, that surplus of novae would make perfect sense, since you'd expect a whole separate galaxy's worth of stars to produce its own steady rate of stellar outbursts, largely independent of whatever rate the Milky Way itself produced. It was an elegant piece of reasoning, even without the final proof a distance measurement would eventually provide. By most accounts, both Shapley and Curtis ended up being partly right and partly wrong. Shapley's larger estimate for the size of the Milky Way itself held up reasonably well against later measurements, while Curtis's insistence that spiral nebulae were separate, external galaxies also turned out to be correct. The debate wasn't actually settled by argument at all that evening in Washington. It was settled a few years later by data. Working at Mount Wilson Observatory, Edwin Hubble identified individual Cepheid variable stars within the Andromeda Nebula itself, applied Leavitt's period luminosity relation to them, and calculated a distance so enormous, far beyond the outer edge of even Shapley's oversized Milky Way, that Andromeda could not possibly be a structure contained within our own galaxy. It had to be an entirely separate island universe of its own, sitting roughly on par with the Milky Way in size and scope. Hubble's Cepheid measurement of Andromeda, made in the years just before he turned to measuring the broader velocity-distance relationship that would make him famous, quietly closed the book on a debate that had occupied serious astronomers for the better part of 2 decades, and it did so using exactly the same tool, exactly the same period luminosity law that Henrietta Leavitt had worked out from Harvard photographic plates roughly a decade earlier, before anyone could even ask whether the universe was expanding. In other words, it first had to be established that there was a universe beyond our own galaxy at all, full of other galaxies, for that expansion to happen between. There's something fitting about the fact that Hubble's name ended up attached to essentially every major milestone in this early story: the settling of the Great Debate through his Andromeda Cepheids, and then the velocity-distance relationship a few years later, given how much of the underlying groundwork had actually been laid by other people first. Leavitt supplied the measuring tool. Slipher supplied the redshift data. Lemaitre supplied the theoretical framework 2 years earlier in a paper almost nobody read. Hubble's genuine and considerable achievement was in bringing these separate threads together at the right observatory, with access to the right instrument at the right moment, and doing so with enough clarity and enough institutional visibility that the wider scientific community finally had no choice but to pay attention. That's not nothing, but it's worth keeping the fuller cast of contributors in view as this story continues, rather than letting one name absorb credit that, by almost every historian's account, was genuinely shared. With all of that in hand, the rest of the observational timeline we've already covered starts to make a lot more sense. It's the reason Hubble could convert Slipher's redshift measurements into an actual velocity-distance relationship in 1929. It's the reason the entire modern cosmic distance ladder, the layered set of overlapping techniques astronomers use to measure distances across the universe today, still starts with Cepheid variables as one of its most important early rungs, calibrated now with even greater precision using parallax measurements from newer instruments, but fundamentally resting on the same period luminosity principle Leavitt worked out from Harvard photographic plates more than a century ago. For more than 3 decades after Hubble and Humeson's 1931 paper, the idea of an expanding, evolving universe with a hot, dense origin remained a serious scientific hypothesis. But it wasn't universally accepted, and it lacked a piece of direct physical evidence that could settle the argument once and for all. That evidence arrived almost entirely by accident. In New Jersey, in the mid-1960s, Arno Penzias and Robert Wilson were radio astronomers working at Bell Labs, and they had access to a large horn-shaped antenna that had originally been built for satellite communication. When they turned it toward the sky to make precise measurements, they kept picking up a faint, persistent hiss of noise, a signal that seemed to come from every direction at once, day or night, regardless of the season. At first, they assumed it was some kind of instrument error or interference. They checked everything. They even climbed into the antenna and removed a bird's nest, hoping that would explain the mysterious noise. It didn't. The signal stayed exactly where it had been all along, uniform, unshakable, coming from everywhere. What Penzias and Wilson didn't know, at least not at first, was that a group of physicists at Princeton University, led by Robert Dicke, had been actively theorizing about exactly this kind of signal. Dicke's team had predicted that if the universe really did begin in an extremely hot, dense state, as Lemaitre's primeval atom idea suggested, then that early heat should have left behind a faint afterglow, a background radiation stretched out by billions of years of cosmic expansion until it settled into the microwave part of the spectrum, at a temperature of just a few degrees above absolute zero. When the two teams finally connected and compared notes, it became clear that Penzias and Wilson, without even intending to, had detected exactly what Dicke's group had been trying to find. Both groups published their results together in 1965, one paper describing the observation, the other explaining what it meant. This radiation is now called the cosmic microwave background, and it stands as one of the most solid, direct pieces of physical evidence for the Big Bang ever obtained. Its discovery was so significant that Penzias and Wilson shared half of the 1978 Nobel Prize in Physics for it, more than a decade after the original detection. Decades of follow-up observation have only strengthened how remarkable that discovery was. In 1989, NASA launched a dedicated satellite called COBE, the Cosmic Background Explorer, specifically to measure this radiation with far greater precision than any ground-based instrument could achieve. COBE accomplished two things that mattered enormously. First, it measured the precise shape of the background radiation spectrum and found that it matches the theoretical prediction for a perfect blackbody so exactly that the measured data points are essentially indistinguishable from the theoretical curve itself. A result so clean, it's often shown to physics students as one of the most beautiful confirmations in the history of the discipline. Second, COBE detected tiny variations in that radiation's temperature from one point in the sky to another, faint ripples amounting to differences of only about 1 part in 100,000. But ripples that turned out to be enormously important, because they represent the seeds of all the large-scale structure that exists in the universe today, the regions of slightly higher density that would eventually collapse under gravity to form the first stars, galaxies, and galaxy clusters. In 2001, NASA followed COBE with a more advanced satellite, the Wilkinson Microwave Anisotropy Probe, or WMAP, which operated until 2010 and dramatically sharpened our picture of those temperature ripples. WMAP's data played a central role in establishing what's now called the Lambda CDM model as the standard working framework of modern cosmology. Lambda, referring to that same cosmological constant Einstein once invented for the wrong reasons, and CDM, standing for cold dark matter, a substance we'll get to shortly. Its temperature today measures 2.725 degrees above absolute zero, known with a precision of just 0.02 of a degree, an almost unimaginably exact measurement of light that has been traveling toward us since the universe was only about 380,000 years old. It's worth understanding why that particular moment, 380,000 years after the Big Bang, is the earliest point in the universe's history any telescope will ever be able to see directly, because it isn't an arbitrary cutoff. Before that point, the universe was still hot and dense enough that matter existed as a plasma, electrons and atomic nuclei flying around independently, rather than bound together into stable neutral atoms. A plasma like that is essentially opaque to light, since free electrons scatter photons constantly, the same way a thick fog scatters a car's headlights and prevents you from seeing very far through it. Only once the universe had expanded and cooled enough to somewhere around 3,000 degrees could electrons finally settle into orbits around atomic nuclei, forming neutral hydrogen and helium atoms in an event cosmologists call recombination. The moment that happened, essentially all at once across the entire universe, the fog lifted. Photons that had been endlessly scattering off free electrons suddenly had a clear path to travel in a straight line, uninterrupted, and it's precisely those photons, released at the moment the universe first became transparent, that Penzias and Wilson picked up on their antenna in New Jersey more than 13 billion years later, stretched by the intervening expansion from a blistering 3,000 degrees down to a mere 2.7 degrees above absolute zero. In a very real sense, no telescope, no matter how powerful, will ever be able to see directly past that moment of recombination, because there's simply no earlier light to receive. Everything before it remains forever hidden behind that same wall of scattering plasma, which is exactly why the discovery of an event as early and as fundamental as cosmic inflation has to be inferred indirectly through its effects on the pattern of ripples imprinted onto this relic light, rather than observed directly the way Penzias and Wilson stumbled onto the light itself. So by the mid-1960s, and increasingly through the following decades, science had two enormously important pieces in place. First, the universe is expanding, established observationally by Hubble and theoretically by Lemaitre and Friedman decades earlier, and grounded in a distance measuring tool built by Henrietta Leavitt. Second, there really was a hot, dense beginning, confirmed by the cosmic microwave background that Penzias and Wilson stumbled into, and that COBE and WMAP later mapped in extraordinary detail. What remained unknown, and what would go on to produce the biggest surprise in modern cosmology, was what the expansion would do next. Would it keep slowing down forever, the way gravity should cause it to, gradually pulling everything back toward a stop? Would it slow down enough to eventually reverse, sending the universe crashing back in on itself in a big crunch? Or would something else happen entirely? Before we get to that surprise though, there's a separate mystery running in parallel through this same period of history, one that doesn't get resolved by anything we've covered so far, and one that turns out to be just as important to the modern picture of the universe as the expansion itself. It concerns not the space between galaxies, but the galaxies themselves, and what appears to be holding them together. In 1933, a Swiss-American astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster, roughly 300 million light-years away, and he did something fairly simple in principle. He measured how fast individual galaxies within the cluster were moving relative to one another, and then calculated how much total mass the cluster would need to contain for its own gravity to hold those fast-moving galaxies together at all, rather than having them fly apart entirely. The number he got back was startling. The gravitating mass required was, by some estimates, at least 400 times greater than the mass that could be accounted for just by adding up the light coming from all the visible stars in the cluster. The method Zwicky used to reach that conclusion rests on a fairly intuitive piece of physics called the virial theorem, which relates how fast objects are moving within a gravitationally bound system to how much total mass that system must contain to keep them from simply flying apart. Picture a cluster of galaxies as something like a swarm of bees held together only by their mutual attraction to each other. If you measure how fast individual bees are darting around within the swarm, you can work out how strong the attraction holding the swarm together needs to be for it to stay intact rather than scattering, and from that, how much total mass is required to generate an attraction of that strength. Zwicky applied exactly this logic to the galaxies within the Coma Cluster, measured their individual velocities, and found they were moving so quickly relative to one another that the cluster's visible mass, added up from all the starlight its member galaxies produced, fell drastically short of what would be needed to hold it together gravitationally. Zwicky concluded there had to be some large quantity of unseen matter holding the cluster together, and he gave it a memorably blunt name in his native German, dunkle Materie, dark matter. A Dutch astronomer named Jan Oort had independently noticed something similarly puzzling about stellar motions closer to home, within our own galactic neighborhood, around the same period. Neither man's work convinced the wider astronomical community at the time. Zwicky's finding, in particular, was treated largely as a curiosity, an oddity confined to one unusual galaxy cluster, and it was more or less set aside for close to 40 years. It took until the 1970s, and the painstaking work of an American astronomer named Vera Rubin, working alongside her collaborator Kent Ford, to turn dark matter from a curious footnote into one of the central pillars of modern cosmology. Rubin and Ford studied what are called rotation curves, essentially graphs plotting how fast stars orbit around the center of a spiral galaxy as a function of how far out from the center they sit. Based on ordinary Newtonian gravity and the distribution of visible matter, stars far out at the edges of a galaxy's visible disk should orbit noticeably slower than stars closer to the bright, dense center, in much the same way that outer planets in our own solar system orbit the Sun more slowly than inner ones. When Rubin and Ford examined the Andromeda Galaxy, and then dozens of other spiral galaxies afterward, they found something that directly contradicted this expectation. The orbital speeds stayed roughly flat, or even ticked up slightly, all the way out to the visible edge of each galaxy's disk and beyond. Rubin herself later described being genuinely puzzled by her own results for months, unsure at first what she was even looking at. The only way to explain flat rotation curves like these, given standard gravity, was if each galaxy contained far more mass than could be seen through any telescope, mass distributed in an extended halo reaching well beyond the visible starlight, quietly providing the additional gravitational pull needed to keep those outer stars orbiting as fast as they do. Rubin's calculations indicated galaxies must contain somewhere between 5 and 10 times more mass than could be directly observed. Her results were confirmed over the following decades by numerous other lines of evidence, including radio observations of hydrogen gas, gravitational lensing studies, and detailed analysis of the cosmic microwave background itself, all pointing toward the same conclusion Zwicky had first stumbled onto decades earlier and that had been largely ignored. An enormous amount of the matter in the universe simply cannot be seen through any electromagnetic instrument we possess, revealing itself only through its gravitational influence on the things we can see. It's worth noting that Rubin herself was notably careful never to claim more than her data actually showed. In interviews late in her life, she pointed out that her observations told her only that there was somewhere between 5 and 10 times more gravitating mass out there than could be directly seen, and that whether this missing mass took the form of some exotic new particle, ordinary but very dim objects like brown dwarf stars, black holes, or something else entirely, simply wasn't a question her rotation curve data alone could answer. That caution has aged well. Decades later, the fundamental nature of dark matter remains unresolved, and Rubin herself, later in her career, expressed some concern that the field had poured an outsized share of its resources into searching for exotic dark matter particles directly, in underground detectors and particle accelerators, while alternative explanations, including a family of modified gravity theories collectively known as MOND, which propose tweaking the law of gravity itself at very low accelerations rather than adding invisible mass, received comparatively little attention or funding by comparison. Most cosmologists today still favor some form of particle dark matter over modified gravity, largely because particle dark matter fits an enormously wide range of independent observations, from galaxy rotation curves to the cosmic microwave background to the bending of light around galaxy clusters, more comfortably than modified gravity theories manage to. Perhaps the single most striking piece of evidence in that wider body of observations came from an object called the Bullet Cluster, first analyzed in detail in 2006. The Bullet Cluster is actually the aftermath of a collision between two separate galaxy clusters, an event that took place roughly 150 million years earlier in a system sitting some 3.7 billion light-years away. When astronomers studied the wreckage using NASA's Chandra X-ray Observatory alongside the Hubble Space Telescope, the European Southern Observatory's Very Large Telescope, and the Magellan telescopes in Chile, they were able to map out three separate things at once, each using a different technique, where the visible galaxies themselves ended up after the collision, where the hot, X-ray emitting gas ended up, since that gas makes up the majority of each cluster's ordinary, visible matter, and collided with itself during the impact the same way two clouds of smoke would collide and slow each other down, and, separately, where the bulk of each cluster's total gravitational mass actually sat, mapped out using gravitational lensing, the bending of light from more distant background galaxies as it passes through the cluster's gravity on its way to Earth. What they found was that the bulk of the gravitational mass, revealed by lensing, sat in a completely different location from the bulk of the visible, X-ray emitting gas. The gas, having collided and dragged against itself during the impact, had been slowed and left behind near the center, while whatever was generating most of the gravitational pull had passed straight through the collision, essentially unaffected, exactly as you'd expect if that mass barely interacts with itself, or with ordinary matter at all, except through gravity, which is precisely the defining property of dark matter. The paper reporting this finding was titled, "Without Much Room for Ambiguity, a direct empirical proof of the existence of dark matter," and it remains one of the most frequently cited pieces of observational evidence in the entire field, precisely because it's difficult to explain through modified gravity alone, without invoking some separate, largely invisible form of mass. There's a second, entirely independent line of evidence supporting the broader Big Bang picture that hasn't come up yet in this video. And it's worth mentioning briefly because it doesn't depend on Hubble's expansion measurements or Penzias and Wilson's cosmic microwave background at all. It's called Big Bang nucleosynthesis, and it concerns the formation of the very lightest chemical elements. According to the standard cosmological model, for a brief window lasting only the first few minutes after the Big Bang, the universe was hot and dense enough for protons and neutrons to fuse together into simple atomic nuclei, before the expansion cooled things down too much for fusion to continue. This process predicts, quite precisely, that the universe should have ended up with roughly 75% of its ordinary matter in the form of hydrogen and roughly 25% in the form of helium, along with tiny, far more specific trace amounts of deuterium and lithium. When astronomers measure the actual abundances of these elements in the oldest, most pristine gas clouds and stars they can find, the numbers line up with the Big Bang's predictions remarkably well. This agreement, achieved using completely different physics and completely different observational techniques from either the expansion measurements or the cosmic microwave background, is generally regarded as the third major pillar of evidence supporting the Big Bang model, standing alongside cosmic expansion and the cosmic microwave background as one of the theory's most important and independently verified successes. But the fact that a serious, ongoing alternative exists at all is a useful reminder that even a pillar of modern cosmology this solid still rests, at its foundation, on inference from gravity's effects, rather than on ever having directly detected the substance itself. Vera Rubin is widely regarded, by much of the astronomical community, as having been snubbed for a Nobel Prize she never received before her death in 2016, a point of ongoing disagreement within the field to this day. In recognition of her contribution, a major new astronomical facility, now under construction and commissioning in Chile, an 8.4-meter wide-field survey telescope designed specifically to help pin down the properties of both dark matter and dark energy, has been named the Vera C. Rubin Observatory in her honor. Under the standard model of cosmology that emerged from combining all of this evidence, dark matter is now understood to make up roughly 27% of the total mass and energy content of the universe, a figure we'll return to shortly alongside its two companions in the cosmic recipe. It behaves gravitationally almost exactly like ordinary matter, clumping together, forming halos, shaping the large-scale structure of galaxies and galaxy clusters, but it does not interact with light in any way we've been able to detect, which is precisely why we call it dark, and precisely why, more than 90 years after Zwicky first proposed its existence, we still don't know what it's fundamentally made of. There's one more major theoretical development from this same broad era worth understanding, because it addresses a pair of puzzles that neither Hubble's expansion nor Penzias and Wilson's cosmic microwave background could fully explain on their own. If the universe really did begin with an extremely hot, dense Big Bang, why does the cosmic microwave background look so remarkably uniform across the entire sky, with temperature differences of only about 1 part in 100,000 between regions that, given the age of the universe and the speed of light, shouldn't have had enough time to ever interact with one another or reach any kind of thermal equilibrium? Physicists call this the horizon problem, and it's a genuinely strange puzzle once you think it through carefully. Look at the cosmic microwave background on opposite sides of the sky, directly away from Earth in one direction and directly away from Earth in the exact opposite direction, and you're looking at two regions of the early universe that, given how much time has passed since the Big Bang, should never have been close enough together for light, or anything else, to travel between them and let them settle into the same temperature, the way two rooms in a house eventually reach the same temperature once a door between them is left open. And yet those two opposite regions match each other in temperature almost perfectly, as though they had somehow been in contact and equilibrated with each other, despite the physical impossibility of that happening under the standard, non-inflationary Big Bang picture alone. And separately, why does the overall geometry of space appear to be so close to perfectly flat, when even a slight deviation from flatness, in either direction, should have been dramatically amplified over billions of years of cosmic expansion into something we'd easily notice today? This second puzzle, the flatness problem, works a little like trying to balance a pencil on its sharpened tip. Even the tiniest deviation from perfectly vertical will, given enough time, topple the pencil dramatically one way or the other. So if you happen to walk into a room and find a pencil still perfectly balanced on its tip, after a very long time had passed, you'd reasonably suspect something had been actively holding it there, rather than assuming it was simply a lucky accident of initial conditions. The universe's geometry presents a strikingly similar puzzle. General relativity predicts that any initial deviation from a perfectly flat geometry should have been magnified enormously by billions of years of ordinary cosmic expansion. And yet precision measurements of the cosmic microwave background show space today to be flat to within a very small margin of error, which strongly suggests whatever set the universe's initial geometry did so with an almost impossibly fine degree of precision, unless some additional mechanism flattened things out afterward. In December of 1979, a young particle physicist named Alan Guth, working at Cornell University, had what he later described as a spectacular realization while puzzling over exactly these kinds of problems. He proposed that in an incomprehensibly brief window, right at the very beginning of the universe's history, somewhere between 10 to the -36th and 10 to the -32nd seconds after the Big Bang, the universe underwent an extraordinarily rapid burst of exponential expansion, growing by some almost inconceivable factor. Estimates in the literature run as high as 10 to the 50th power, in a fraction of a second, far too brief for human intuition to grasp in any meaningful way. Guth gave his first public seminar on the idea in January of 1980, and formally proposed the theory the following year while at Stanford. He called this brief, explosive burst of expansion inflation, and it elegantly solves both puzzles at once, because regions of the early universe were, briefly, close enough together to interact and reach a common temperature before inflation flung them apart to enormous, causally disconnected distances. The cosmic microwave background ends up looking remarkably uniform across the whole sky, exactly as observed. And because any large-scale curvature the universe might have started with gets stretched out and effectively flattened by that same explosive expansion, the same way stretching a balloon large enough would make any small patch of its surface look essentially flat, inflation naturally explains why space today appears so close to perfectly flat on the largest scales we can measure. Inflation theory has become widely accepted within cosmology since Guth introduced it, and in 2014 he shared the Kavli Prize in Astrophysics along with two other physicists, Alexei Starobinsky and Andrei Linde, who had developed closely related ideas around the same period, for pioneering the theory of cosmic inflation. It's worth being straightforward, though, about the fact that inflation remains, in certain respects, more of a theoretical framework than a fully proven fact. Some physicists, mathematicians, and philosophers of science have raised genuine criticisms over the years, arguing that certain versions of inflationary theory make predictions that are difficult or impossible to test directly, which is a real and ongoing point of debate within the field, rather than a settled matter. What inflation does successfully do, and what makes it useful regardless of these debates, is explain, cleanly and elegantly, two features of the observed universe, its remarkable uniformity and its remarkable flatness, that are otherwise very difficult to account for. Guth's own thinking about inflation carries one more implication worth sitting with, strange as it sounds. Much of his later research has focused on the question of whether inflation, once it starts, ever really stops everywhere at once, or whether it keeps going forever in some regions even as it ends in others, a property physicists call eternal inflation. If that's correct, our own observable universe, everything we've been describing in this video, the 93 billion light-year bubble containing every galaxy we could ever hope to see, might be just one relatively small region where inflation happened to end early enough to let stars, galaxies, and eventually us come into being, while inflation continues indefinitely elsewhere, perpetually spinning off other such regions, each potentially with its own distinct physical conditions. Guth himself has described this as one of the genuinely mind-bending consequences of taking his own theory seriously, and other physicists working in this area have gone so far as to describe the resulting picture, a universe that may have essentially created itself and keeps creating more copies of itself out of nothing, as cosmology's version of an ultimate free lunch. It's a genuinely speculative extension of inflationary theory rather than a confirmed finding, and it's not something current instruments can test directly, but it's a fair illustration of just how far the implications of a single theoretical insight from a snowy night in December of 1979 have ended up reaching. With all of that theoretical and observational scaffolding in place, the expansion of space, the hot, dense origin, the unseen dark matter shaping galaxies, the inflationary explanation for the universe's uniform, flat geometry, cosmologists by the 1980s and early 1990s felt they had a fairly complete, if still incomplete in the details, picture of how the universe worked. The leading assumption was that gravity, acting on all the matter in the universe, ought to be gradually decelerating the expansion that Hubble and Lemaitre had discovered decades earlier. Every galaxy pulls on every other galaxy, and that mutual pull should act like a brake, slowing the rate at which everything spreads apart. The only real question, as far as most cosmologists were concerned, was how much the expansion was slowing down, and whether there was enough matter in the universe to eventually halt it and reverse it entirely. Two independent research teams set out in the 1990s to measure exactly that deceleration, and in doing so, they stumbled onto one of the strangest and most consequential findings in the history of physics. The first team, called the Supernova Cosmology Project, was founded in 1988 by Saul Perlmutter, working out of the Lawrence Berkeley National Laboratory and the University of California, Berkeley. The second team, called the High Z Supernova Search Team, began its work in 1994 under the leadership of Brian Schmidt at the Australian National University, and was later joined by a researcher named Adam Rees, who would go on to become the lead author of one of the two teams' defining papers. Interestingly, one astronomer, Alex Filipenko of UC Berkeley, actually worked with both of these rival teams at different points, giving him a rare front-row seat to competing efforts chasing the exact same question. Both teams used the same basic tool, a particular kind of exploding star called a Type Ia supernova. These explosions are useful to cosmologists because they tend to reach almost exactly the same peak brightness every time they occur, regardless of where or when they happen. That consistency makes them what astronomers call a standard candle, an object whose true brightness is known well enough that comparing it to how bright it appears from Earth lets you calculate precisely how far away it is. The same basic logic Henrietta Leavitt had established for Cepheid variables decades earlier, just applied to a far brighter, far more distant class of object, capable of being seen across billions of light-years rather than mere millions. Combine that distance measurement with the redshift of the light coming from the galaxy that hosted the supernova, and you can map out how the universe's expansion rate has changed at different points in cosmic history, effectively looking backward in time the farther out you look. It's worth understanding what a Type Ia supernova actually is, because the reason these particular explosions make such reliable standard candles comes down to a fairly elegant piece of stellar physics. These supernovae come from white dwarfs, the dense, burned-out cores left behind after a sun-like star has exhausted its nuclear fuel, typically sitting in a binary system alongside a companion star. Over time, the white dwarf siphons material off its companion, slowly gaining mass, and there's a well-defined ceiling to how massive a white dwarf can become before it can no longer support itself against its own gravity, a threshold called the Chandrasekhar limit, sitting at roughly 1.4 times the mass of our Sun. When an accreting white dwarf approaches that limit, it triggers a runaway thermonuclear reaction that tears the entire star apart in one explosive burst, producing a large quantity of radioactive nickel-56. That nickel-56 doesn't stay nickel for long. It decays first into radioactive cobalt-56, and the cobalt in turn decays into stable iron-56. And it's the energy released across that two-step radioactive decay chain, rather than the initial explosion itself, that actually powers the visible glow of the supernova as it brightens and then gradually fades over the following weeks, giving each Type Ia supernova its own distinctive, predictable light curve. Because so many of these explosions are triggered by white dwarfs reaching essentially the same mass limit, they tend to release almost exactly the same amount of energy and reach almost exactly the same peak brightness every time, give or take a well-understood correction, based on how quickly each individual supernova's brightness rises and falls, a calibration researchers call the Phillips relation, which lets astronomers correct for the small remaining differences between individual explosions and pin down relative distances to within a few % accuracy. That combination, a genuinely astrophysical reason for consistent brightness, plus a reliable mathematical correction for the small variations that do exist, is what allowed both the Supernova Cosmology Project and the High Z Supernova Search Team to trust their distance measurements enough to notice something as subtle and as surprising as an accelerating expansion in the first place. It's worth stepping back here to notice how directly this connects to everything covered earlier in this video, because Type Ia supernovae don't actually stand on their own as a distance measuring tool. They're one rung, admittedly a very useful one, on what astronomers call the cosmic distance ladder, a layered, overlapping set of techniques where each rung is calibrated using the rung below it. Nearby stars get their distances measured directly, through parallax, the tiny apparent shift in a star's position caused by Earth's own orbit around the Sun. Those parallax distances are then used to calibrate the true brightness of Cepheid variable stars sitting at those same, already known distances, refining the period luminosity relation Henrietta Leavitt first worked out in 1912. Those calibrated Cepheids are then found in more distant galaxies, close enough for both a Cepheid measurement and a Type Ia supernova to be observed in the very same galaxy, which lets astronomers calibrate the true brightness of Type 1a supernovae using the Cepheid distance as a known reference point. Only after all of that calibration is locked in can astronomers point their instruments at supernovae so distant that no individual Cepheid could ever be resolved within their host galaxies, and still trust the resulting distance measurement. Every step in that ladder depends on the step below it holding up under scrutiny, which is exactly why the James Webb Space Telescope's re-examination of the Cepheid rung, confirming Hubble Space Telescope's original measurements were accurate, mattered so much to the Hubble tension discussed later in this video. If that particular rung of the ladder had turned out to be flawed, the entire structure built on top of it, all the way up to the supernova measurements underlying the discovery of dark energy itself, would have needed to be reconsidered. Both teams expected to find evidence of deceleration, confirmation that gravity was doing exactly what everyone assumed it should be doing. Instead, in 1997 and 1998, both teams independently found the opposite. The most distant supernovae were fainter, and therefore farther away, than they should have been if the expansion were simply slowing down under gravity's pull. The only way to explain that discrepancy was if the expansion of the universe wasn't decelerating at all, it was accelerating. Perlmutter later described just how reluctant his team was to accept their own result. The chain of analysis was so long, he said, that at first they didn't trust it, but the more they checked it, the more it refused to go away. The High-Z team, working completely independently with its own set of supernovae, arrived at the same startling conclusion at nearly the same time. Two separate teams, using separate data, separate instruments, and separate analysis pipelines, converged on an answer nobody had expected and almost nobody wanted. The finding was so significant that the journal Science jointly named it the breakthrough of the year for 1998. An accelerating expansion implies something specific and strange, some kind of force or substance, spread uniformly throughout the universe, that acts in the opposite direction to gravity, pushing everything apart rather than pulling it together. Nobody knew, and frankly nobody still knows for certain, exactly what that substance is. Scientists gave it a name anyway. They called it dark energy, and in a strange historical echo, the mathematical tool used to describe it, that same cosmological constant Einstein invented in 1917 for entirely the wrong reason and later disowned, turned out to be almost exactly the right tool for the job, just deployed for the opposite purpose Einstein originally intended. The discovery reshaped how physicists think about the ultimate fate of the cosmos, and it was significant enough that, in 2011, Perlmutter, Schmidt, and Rees were jointly awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Perlmutter received half of the prize, worth roughly $1.4 million in total, while Schmidt and Rees shared the other half. On learning of the award, Perlmutter said simply that he was delighted and excited. The nature of dark energy itself has since been described as one of the most important problems facing 21st century physics, precisely because, more than 2 decades after its discovery, we still don't know what it fundamentally is. One reason physicists find dark energy so uncomfortable to sit with is a separate but closely related puzzle called the cosmological constant problem, sometimes described, without much exaggeration, as the worst theoretical prediction in the history of physics. The most natural candidate for what dark energy actually is, physically, comes from quantum field theory, which predicts that empty space itself, the vacuum, should contain a certain baseline amount of energy, arising from particles and fields constantly flickering in and out of existence, even in a region with nothing else in it. If you calculate how much of that vacuum energy quantum field theory predicts, and compare that number to the actual, measured value of dark energy inferred from supernovae, the cosmic microwave background, and large-scale structure surveys, the two numbers disagree by roughly 120 orders of magnitude, meaning the theoretical prediction is off by a factor of 1, followed by about 120 zeros. It is difficult to overstate how enormous that gap is. If the vacuum energy really were as large as the naive quantum calculation suggests, the repulsive push of empty space would have been so overwhelming that it would have ripped the early universe apart before a single star or galaxy ever had the chance to form. Since we're obviously here to ask the question, the real value has to be almost but not quite, precisely zero, small enough to allow galaxies and stars, and eventually us, to exist. Yet, not exactly zero, since dark energy demonstrably does something, accelerating the expansion. Perlmutter, Schmidt, and Rees discovered in 1998. Nobody currently has a fully accepted explanation for why the actual value lands in that impossibly narrow, seemingly fine-tuned range, and it remains one of the deepest unsolved problems sitting underneath everything else discussed in this video. A handful of theorists have floated the idea, unsettling in its own right, that the value simply has to sit where it does, purely because a universe with a much larger vacuum energy would never have allowed galaxies, stars, or observers capable of measuring any of this to exist in the first place, an argument known as the anthropic principle, though plenty of physicists find that explanation deeply unsatisfying as a substitute for a genuine physical mechanism, and the debate over whether it counts as an explanation at all remains very much unresolved. According to the standard cosmological model that scientists use today, called lambda CDM, a name worth unpacking briefly since it will keep coming up for the remainder of this video, dark energy makes up roughly 68% of everything in the universe. The lambda in that name refers directly back to Einstein's own cosmological constant, the same symbol he used in his 1917 equations, repurposed now to describe dark energy's steady, unchanging push, while CDM stands for cold dark matter, describing the slow-moving, gravitationally clumping substance Zwicky and Rubin's work eventually forced the field to take seriously. Dark matter, the completely separate mystery uncovered by Zwicky and later confirmed by Rubin, accounts for about 27%. Ordinary matter, the protons, neutrons, electrons, atoms, stars, planets, and people, all of the stuff we can actually see and touch, makes up less than 5% of the total. The precise figures from the Planck satellite's 2013 results put this at 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. Put another way, the overwhelming majority of everything that exists is made of something we cannot directly observe and do not fully understand, and it took two entirely separate scientific mysteries, one concerning galaxies that spin too fast for their visible mass, the other concerning an expansion that speeds up instead of slowing down, to reveal that 95% of the universe's content was hiding from us in plain sight the whole time. It's worth sitting with what that less than 5% figure actually contains, because it's easy to assume it must at least cover everything familiar, and it doesn't, not entirely. That slim, ordinary matter slice includes every star, every planet, every galaxy's worth of gas and dust, every living thing, every atom in every book, building, and body that has ever existed. And yet the overwhelming majority of even that small ordinary matter percentage isn't found in stars or planets at all. Most of it exists as thin, diffuse gas scattered between galaxies, largely hydrogen and helium left over from Big Bang nucleosynthesis, never having condensed into anything as organized as a star. Stars themselves, along with everything orbiting them, including every planet ever discovered, make up only a small fraction of even that already small 5% slice. The plain implication, and it's one cosmologists have had to get comfortable with over the past few decades, is that almost everything genuinely interesting to human beings, every sunset, every ocean, every person who has ever lived, is built from a component of the universe so minor that, measured against the totals, it barely registers as a rounding error. This is also where we get our modern estimate for the age of the universe, a figure worth restating plainly given how central it is to everything else in this video. 13.8 billion years, give or take a small margin of refinement across successive satellite missions. Precise measurements from the European Space Agency's Planck satellite, launched in 2009 and operating for about 4.5 years, refined the age of the universe to 13.82 billion years, roughly 100 million years older than an earlier estimate derived from NASA's WMAP mission. That revision happened because Planck found the universe expanding just slightly more slowly overall than previously assumed, which pushes the calculated starting point further back in time. Here's where the story gets genuinely strange, and where the title of this video actually starts to earn its meaning. If you take that age, 13.8 billion years, and you multiply it by the speed of light, you might expect the observable universe to be about 13.8 billion light-years across in any direction. It isn't. It's roughly 46.5 billion light-years from Earth to the edge of what we can observe, in every direction, making the observable universe a sphere about 93 billion light-years across. That number seems to break the most basic rule in physics, the idea that nothing can travel faster than light. But nothing actually is. The light we're receiving today from the most distant visible objects left its source roughly 13.8 billion years ago, when that source was much, much closer to us than it is now, only a few tens of millions of light-years away in some estimates. But during the nearly 14 billion years that light has spent traveling toward us, the space between us and that source has been continuously stretching, expanding the whole time the light was in transit. So by the time that ancient light finally reaches our telescopes today, the object that originally emitted it has been carried, by the expansion of space itself, to a location roughly 46 billion light-years away. It isn't the light breaking the speed limit, it's the space between us and the light's origin doing the stretching. The same raisin-bread expansion we described earlier, just accumulated over nearly the entire history of the universe. And that stretching effect gets stranger and more consequential the farther out you look. There's a specific threshold distance, roughly somewhere between 16 and 18 billion light-years from us, depending on exactly how you define it, beyond which galaxies are already receding from us faster than the speed of light, purely as a result of the expansion of space itself, not because those galaxies are physically moving through space at some impossible velocity. This isn't a violation of relativity, because it's the space itself expanding, not any object moving through that space faster than light. Einstein's speed limit applies to how fast something can travel through space, from one nearby point to another, and it has never been broken by anything ever observed. But the rule was never meant to constrain how quickly the space in between two points can grow, and general relativity, the very same theory that gave us the Friedmann equations, the Big Bang, and everything else in this story, fully permits the distance between two sufficiently far apart points to increase faster than light could cross it, precisely because no actual object or signal is being asked to make that crossing. It's a subtle enough distinction that it trips up plenty of people encountering it for the first time, and it's worth repeating plainly. Nothing is moving through space faster than light in this picture. Space itself is simply growing quickly enough that the distance between 2 points can increase at a rate exceeding light speed, even while every individual object embedded within that space stays perfectly still relative to its own immediate surroundings. But the practical consequence is real and permanent. Any galaxy beyond that distance is already moving away from us faster than light could ever cross the growing gap between us. Their light, emitted right now, in this moment, will never reach Earth. Not in a million years, not in a trillion years, not ever. This means that even though the observable universe looks enormous, roughly 93 billion light-years across, only a small fraction of that volume is something we could ever actually travel to, even hypothetically, even at the speed of light. Estimates suggest that today, only about 6% of the volume of the currently observable universe lies within our permanently reachable limit. The other 94%, everything beyond that threshold, is already forever out of reach, receding from us faster than any signal, any spacecraft, any form of communication could ever catch up to it. And this isn't a static situation. It's actively getting worse, year by year, as the accelerating expansion continues to do its work. Because dark energy keeps pushing space apart at an ever-increasing rate, more and more galaxies are crossing that threshold of permanent unreachability all the time. Every single year, by some estimates, hundreds of millions of additional stars, distributed across what might be hundreds of individual galaxies, cross over from being theoretically reachable to being permanently, irrevocably out of reach. Given that the observable universe is estimated to contain something on the order of 2 sextillion stars in total, and only around 6% of them, something like 120 quintillion, are presently within our reachable limit, the scale of what's slipping away from us every single year is genuinely difficult to hold in your head. 2 sextillion is a 2 followed by 21 zeros, a number so far removed from anything encountered in ordinary life that comparisons tend to break down almost immediately. But it's worth trying one anyway. There are more stars within just the reachable 6% of the observable universe than there are grains of sand on every beach and desert on Earth combined, by most standard estimates of the planet's total sand content. And that's only the fraction we could still theoretically visit. The other 94%, the vast majority of everything within the observable universe, already sits forever beyond that limit, receding from us at speeds no future technology, however advanced, could ever outrun. Run the clock forward far enough, and the picture becomes almost unbearably lonely. According to calculations based on our current understanding of dark energy's behavior, in roughly another 112 billion years from now, every single galaxy currently outside our own local group, which includes the Milky Way, Andromeda, and a modest handful of smaller neighboring galaxies, will have receded beyond the point where it could ever be reached again, even in principle, even by light itself. What remains, after that unimaginable stretch of time, will be whatever our own local group has merged into by then, sitting essentially alone in an otherwise empty, ever-expanding cosmos. It's worth noting that this 112 billion-year timescale, staggering as it already sounds, is still comparatively short measured against the far larger numbers that show up later in this video when we get to the universe's ultimate long-term fate, where the relevant timescales stretch out to trillions of years and beyond. Losing access to every other galaxy in the universe turns out to be one of the earlier milestones in an extremely long and increasingly strange future, not the final one. Now, it's worth pausing here to flag something important, because not everyone in the scientific community frames this the same way, and there's a genuine, interesting disagreement buried inside this topic. Some astrophysicists push back hard on the idea that galaxies are simply disappearing from view. One argument, made by the astrophysicist Ethan Siegel, points out that there's a meaningful difference between a galaxy becoming permanently unreachable and a galaxy actually vanishing from what we can observe. Because light from extremely distant galaxies has had more and more time to reach us as the universe ages, Siegel argues that the total number of galaxies we can potentially observe, given good enough instruments and enough patience, will actually keep growing for a very long time into the future, possibly more than doubling from roughly 2 trillion galaxies today to as many as 4.7 trillion eventually observable galaxies far into the future. His point isn't that expansion isn't happening, or that the reachability problem isn't real. It's that observable and reachable are two different concepts that get conflated in popular explanations, and depending on which one you're talking about, the story sounds either encouraging or bleak. Both framings are using the same underlying physics. They're just answering slightly different questions, and it's a useful reminder that even among experts who agree completely on the underlying data, the way you choose to frame a result can lead to genuinely different conclusions about what that result actually means for us. It's worth sitting for a moment with what this would actually look like from the inside, so to speak, rather than just as an abstract set of numbers. An observer, living far enough in the future, on some world orbiting a star within our own merged local group, wouldn't necessarily witness anything sudden or dramatic. Individual galaxies wouldn't blink out of existence overnight. Instead, their light would simply grow dimmer and redder over enormous stretches of time, stretched further and further by the accumulating expansion of the space between here and there, fading gradually into undetectability, the way a radio signal fades into static as you drive farther from the transmitter. A civilization arising late enough in cosmic history, billions of years after our own era, might look out at the night sky and see only their own galaxy's stars, with no evidence at all that other galaxies had ever existed, no cosmic microwave background left bright enough to detect, no observational trail leading back to a Big Bang. They would have every reason, based purely on what remained observable to them, to conclude that their galaxy was the entire universe, in a strange echo of exactly what Harlow Shapley once argued about our own Milky Way back in 1920, except in their case, unlike Shapley's, there would be no Vesto Slipher, no Henrietta Leavitt, no Edwin Hubble left with any way to prove them wrong. We happen to be living at a moment in cosmic history when the evidence for an expanding, evolving universe with billions of visible companion galaxies is still there to be found, still written across the sky in redshifted starlight and residual microwave static. And there's a real possibility that this observational window won't stay open forever. That distinction matters, But it doesn't change the central mystery at the heart of this entire topic, which is that we still don't actually know, with anything close to certainty, exactly how fast this expansion is happening right now. And that brings us to the problem that has come to define modern cosmology more than any other: the Hubble tension. Here's the shape of the disagreement. There are, broadly speaking, two completely independent ways of measuring the universe's current expansion rate, a number cosmologists call the Hubble constant. The first method looks at relatively nearby objects, things like Cepheid variable stars and Type 1a supernovae, essentially building what's called a cosmic distance ladder, calibrating distances step by step out into the local universe and measuring how fast things are receding from us today. This is often called the late universe or local method, and it consistently produces a value close to 73 kilometers per second per megaparsec. The most precise recent version of this measurement, published by the SH0ES team led by Adam Rees in 2022, using around 300 high redshift Type 1a supernovae, put the number at 73.04, with an uncertainty of just about 1 kilometer per second per megaparsec in either direction. The second method works completely differently. It looks not at nearby stars and galaxies at all, but at the cosmic microwave background itself, that ancient afterglow discovered by Penzias and Wilson and mapped in such precise detail by COBE and WMAP. And it uses a detailed cosmological model to work forward from the conditions of the very early universe to a predicted expansion rate today. This is called the early universe method, and it consistently produces a noticeably lower number, close to 67.4 kilometers per second per megaparsec, based primarily on the European Space Agency's Planck satellite data. The gap between those two numbers, 73 versus 67.4, might not sound enormous at first glance. It's roughly a 9% difference, but in scientific terms, this discrepancy has grown so statistically significant, exceeding what's called 5 sigma confidence, that it's become extremely difficult to explain away as simple measurement error or coincidence. It's worth understanding what that 5 sigma threshold actually represents, since it comes up again later in this video in a different context. Physicists use the term sigma to describe how far a result sits from what you'd expect, purely by chance, if there were no real underlying effect at all. A 5 sigma result corresponds, roughly, to odds of about 1 in a few million that the discrepancy is simply a random statistical fluke, the level of certainty physicists generally require before they're willing to call something a genuine, established discovery rather than merely a suggestive hint. The Hubble tension has cleared that same demanding bar, the same threshold used to certify discoveries like the Higgs boson, which is precisely why so many cosmologists now treat it as a real, physical puzzle demanding an explanation, rather than a statistical coincidence likely to quietly resolve itself as measurements improve. Two completely independent methods, using entirely different physics, entirely different instruments, and entirely different underlying assumptions, keep landing on two different answers, and the harder scientists work to eliminate possible sources of error, the more stubbornly that gap refuses to close. It's worth pausing here to explain why this is even measured this way in the first place, rather than simply watching the expansion happen directly. On the timescale of a single human life, or even the entire span of recorded human history, the universe's expansion rate doesn't change by any amount we could ever hope to detect through direct, repeated observation. You cannot point a telescope at a single galaxy, wait a few decades, and watch its recession speed visibly shift. Instead, cosmologists exploit the fact that light takes time to travel, which means looking at objects farther away is equivalent to looking further back into cosmic history. A nearby galaxy shows us the universe's expansion rate more or less as it is today, while a galaxy whose light took billions of years to reach us shows the expansion rate as it was billions of years ago. By comparing many objects at many different distances, astronomers effectively assemble a time-lapse of the universe's expansion history, without ever having to wait around for it to visibly change. That's why both competing camps in the Hubble tension debate rely on such fundamentally different types of objects and methods, one calibrating a distance ladder through progressively more distant nearby objects, the other extrapolating forward from the very edge of the observable universe. And it's why any subtle, systematic flaw hiding inside either one of those methods becomes so difficult to track down. Many people initially hoped the James Webb Space Telescope, with its dramatically improved resolution and sensitivity compared to the older Hubble Space Telescope, would settle the argument once and for all, perhaps by revealing that the local, nearby measurements had been thrown off by something mundane, like interstellar dust, interfering with the light from Cepheid stars and making them appear dimmer and therefore farther away than they truly are, or by overcrowded star fields blending a Cepheid's light together with its unresolved neighbors and throwing off the brightness measurement that the entire period luminosity calculation depends on. Both of these were serious, well-reasoned candidate explanations, not idle speculation, precisely the kind of subtle, systematic error that could plausibly explain a 9% discrepancy without requiring any new physics at all. That's not what happened. When the James Webb Space Telescope examined the same Cepheid variable stars used in the local measurements, it confirmed that the original Hubble Space Telescope measurements had been accurate all along. Rather than resolving the tension, James Webb actually deepened it, by ruling out one of the most plausible mundane explanations for why the two methods might disagree. Since then, the puzzle has only grown more layered. In 2025, a combined analysis using Planck data alongside two ground-based instruments, the South Pole Telescope and the Atacama Cosmology Telescope, produced a refined early universe estimate of 67.24 kilometers per second per megaparsec, essentially confirming the lower value with even greater precision. Meanwhile, the astronomer Wendy Friedman took an entirely different approach to the local, late universe side of the measurement, one that sidesteps Cepheid variable stars altogether. Rather than relying on the pulsating stars Henrietta Leavitt first studied, Friedman's method uses red giants, stars nearing the very end of their lives, at the specific moment they undergo a sudden, dramatic internal change, a rapid jump to core temperatures around 100 million degrees, accompanied by an equally sudden drop in the star's brightness. Because that particular transition happens at almost exactly the same true luminosity in every red giant that reaches it. Regardless of which galaxy it happens to sit in, it functions as yet another kind of standard candle, one built on entirely different underlying physics, and crucially, one that isn't vulnerable to the same potential sources of error, like interstellar dust or overcrowded star fields, that affect Cepheid measurements. Using this red giant method alongside other calibration techniques, Friedman's 2025 measurement produced an independent estimate of 70.4 kilometers per second per megaparsec, a number that sits almost exactly between the two rival camps, muddying the picture even further rather than clarifying it, since it's not quite low enough to fully vindicate the early universe camp, and not quite high enough to fully vindicate the local, Cepheid-based camp either. Even a completely different technique, using the afterglow of a neutron star merger detected through gravitational waves back in 2017, produced yet another independent estimate, 67.0 kilometers per second per megaparsec, broadly consistent with the lower, early universe value, though with a wider margin of error. As of the most recent reporting available, from around December 2025, cosmologists describe the Hubble tension as the single most significant unresolved puzzle in the entire field. Nobody knows for certain whether the explanation is some subtle, still undiscovered systematic error hiding in one or both measurement techniques, or whether it points towards something far more exciting and far more unsettling, that our standard model of cosmology, the framework that has successfully explained an enormous range of observations for decades, might actually be incomplete in some fundamental way. Take a moment to appreciate just how unusual this situation actually is within science more broadly. It isn't that scientists disagree about some minor, poorly measured quantity out at the ragged edge of what current instruments can detect. Both competing measurements of the Hubble constant are individually extremely precise, each backed by rigorous, independently repeated observations, each scrutinized for years by rival research groups actively looking for the other side's mistakes. The early universe measurement rests on the cosmic microwave background, quite possibly the most thoroughly cross-checked signal in all of observational science, mapped in exquisite detail by 3 separate satellite missions across more than 3 decades. The late universe measurement rests on a distance ladder built from Cepheids and supernovae that has itself been independently validated by entirely different methods, including the red giant approach and the neutron-star merger approach mentioned earlier. This isn't a case of one side clearly having better data than the other. Both sides have excellent data. They simply refuse to agree, and that persistent, well-documented refusal to agree is precisely why so many cosmologists now suspect that something genuinely new about how the universe works, some physics not yet accounted for in the standard model, may be hiding inside that gap between 67 and 73. There's a small, almost poetic irony worth mentioning here, because it connects directly back to where this story started. Edwin Hubble's own original 1929 estimate for this exact same number, the expansion rate now named after him, was 500 kilometers per second per megaparsec, wildly higher than either of the modern figures scientists are currently arguing over, due to distance measurement errors common in that early era of astronomy. In a sense, the entire history of this field since 1929 has been one long process of narrowing that number down, from Hubble's wildly overestimated 500, through Lemaitre's earlier estimates in the 500s and 600s, down through decades of refinement, only to arrive, nearly a century later, at two competing, far more precise answers that still can't agree with each other. The measurement has gotten enormously more accurate. The disagreement, strangely, hasn't gone away. It's just moved to a far more exacting, far more scrutinized level of precision. And as if that weren't enough uncertainty for one field of science to handle, an entirely separate and equally significant question has opened up in just the past 2 years, concerning dark energy itself. Remember, dark energy is usually modeled as what's called a cosmological constant, meaning its strength, its outward push against gravity, is assumed to stay exactly the same throughout the history of the universe and into the future. That assumption has now been called into question by results from an instrument called DESI, the Dark Energy Spectroscopic Instrument, mounted on the Nicholas U. Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. DESI is a massive international collaboration involving more than 900 researchers spread across over 70 institutions worldwide. Its purpose is to build the largest three-dimensional map of the universe ever constructed, using the positions and redshifts of millions of galaxies and quasars to trace how the universe's structure and its expansion has evolved across billions of years of cosmic history. The specific technique underlying much of DESI's measurement is worth understanding because it's a genuinely elegant piece of physics in its own right. In the extremely early universe, before atoms had even formed, ordinary matter and light existed together as a hot, dense plasma, and pressure waves, essentially sound waves, rippled through that plasma the same way sound ripples through air. When the universe cooled enough for neutral atoms to form, roughly 380,000 years after the Big Bang, those pressure waves froze in place, leaving behind a faint, consistent imprint on how matter ended up distributed through space. A very slight tendency for galaxies to be found at one particular characteristic separation distance from each other more often than at other distances, rather like the frozen ripples left in sand after a wave recedes from a beach. Because this characteristic distance can be calculated precisely from the physics of the early universe and the cosmic microwave background, it functions as what cosmologists call a standard ruler, an object of known size that can be measured at different distances, and therefore different points in cosmic history, to work out how much the universe has expanded between one era and another. This method, called Baryon Acoustic Oscillation Measurement, or BAO for short, is the central technique behind DESI's three-dimensional galaxy map, and it's a completely independent way of tracking cosmic expansion from the supernova and cosmic microwave background methods described earlier in this video, which is precisely why its results carry so much weight when they start suggesting something as significant as dark energy actually changing over time. In 2024, DESI's first year of data offered an early hint that dark energy might not be constant after all, that its strength might actually be changing over time, weakening as the universe ages, rather than remaining fixed. Then, on March 19, 2025, the DESI collaboration released a far more powerful follow-up analysis, incorporating nearly 15 million of the best measured galaxies and quasars, more than double the dataset used in their first release, and tracking dark energy's influence across the past 11 billion years of cosmic history. The results strengthened, rather than weakened, the earlier hint. Taken entirely on its own, DESI's newest data remains broadly consistent with the standard model, the simple cosmological constant version of dark energy. But when combined with other independent measurements, including data on the cosmic microwave background, supernovae, and weak gravitational lensing, the evidence increasingly points toward dark energy's influence actually weakening over time, rather than staying fixed, exactly as the standard model assumes it should. The scientists involved were careful, in public statements, not to overstate their certainty, and that caution itself is worth noting, since it's exactly the kind of restraint that separates a credible, still-developing scientific result from an overhyped headline. Alexey Lyoto-Harnet, a co-spokesperson for the DESI collaboration and professor at UC Santa Cruz, described the findings as deeply intriguing and said it was exciting to think that researchers might be on the cusp of a major discovery about dark energy and the fundamental nature of the universe. Seshadri Nadathur, a co-chair of one of DESI's working groups at the University of Portsmouth, put it plainly. It's not just that the data continue to show a preference for evolving dark energy, but that the evidence supporting that preference is stronger now than it was before. Andrei Kuchev, a postdoctoral researcher at Berkeley Lab, offered a nice way of framing the uncertainty itself, saying that scientists are in the business of letting the universe tell them how it works, and maybe the universe is telling them it's more complicated than they thought it was. A sentiment that, in hindsight, could just as easily have been said by Perlmutter or Schmidt in 1998, by Rubin in the 1970s, or by Lemaitre himself back in 1927, each of them arriving at a result. The universe seemed determined to make them work far harder to accept than they had originally expected. Another researcher on the team, Etienne Bertin, was careful to note there is absolutely no certainty yet about any of this, but he expects a much clearer picture to emerge within roughly the next 5 years, as more data continues to come in. That specific estimate is worth taking seriously precisely because it comes from someone working with the data directly, aware of exactly how much more precision the next few years of observation are expected to add, rather than someone speculating from the outside about when an answer might arrive. The announcement generated an enormous amount of attention outside the scientific community as well. Within a few weeks of the March 2025 release, more than 1,500 separate news articles about the findings had appeared across 67 different countries, a reflection of just how deeply the question of what our universe is fundamentally made of and how it behaves still captures public imagination nearly a century after Lemaitre and Hubble first suggested it was expanding at all. It's worth reflecting for a second on why a single instrument's data release, describing a result its own team was careful to call merely intriguing rather than confirmed, could generate that kind of global attention in the first place. Part of the answer is simply the size of the stakes involved. Dark energy makes up more than 2/3 of everything that exists, and the assumption that it behaves as a constant, unchanging cosmological term has quietly underpinned essentially every major cosmological calculation for the past quarter century, from the age of the universe to predictions about its ultimate fate. A confirmed finding that this assumption is wrong wouldn't just tweak some minor parameter in an equation somewhere. It would mean the entire lambda CDM framework, the standard model referenced throughout this video, needs a fundamental update, and it would very likely mean a Nobel Prize for whichever team or individual manages to pin down exactly how and why dark energy changes. That combination, an assumption this foundational, a discovery this consequential, and a result still sitting just shy of the level of certainty physicists require before calling something settled, is precisely the kind of story that draws attention well beyond the usual audience for cosmology news, and it's part of why DESI's own scientists were so careful, in every public statement quoted earlier in this video, to describe their findings as intriguing hints rather than a confirmed breakthrough. DESI isn't operating in isolation, and it's worth understanding what else is coming, because an entire generation of new observatories has been built or is being built specifically to chase down this exact mystery. The European Space Agency launched its Euclid satellite in 2023, a mission costing roughly €1.4 billion, designed to survey an enormous portion of the sky, roughly 14,500 square degrees, measuring the shapes, positions, and distances of billions of galaxies, along with precise spectroscopic redshifts for tens of millions of them, all in service of narrowing down exactly what dark energy is and whether it behaves the way the standard cosmological constant model predicts. Meanwhile, in Chile, the Vera C. Rubin Observatory, the same facility named in honor of the astronomer whose rotation curve work confirmed dark matter's existence, began commissioning its enormous 3.2 gigapixel camera in 2025, ahead of a 10-year survey called the Legacy Survey of Space and Time, which is expected to independently test the same evolving dark energy hints DESI has been reporting, using a completely different observational technique based on how the light from distant galaxies gets subtly bent by the gravity of everything sitting in front of it. And NASA's Nancy Grace Roman Space Telescope, carrying a 2.4-meter mirror, comparable in size to the Hubble Space Telescopes, is being built specifically to study dark energy's effect on cosmic expansion in even greater detail, with a launch expected around the middle of this decade's back half. One astronomer quoted in coverage of these missions, Ofer Lahav, put the stakes in refreshingly blunt terms. The whole community, he said, is spending billions of dollars to see if the equation of state parameter describing dark energy, a number physicists call W, is exactly equal to -1, the value predicted by a simple, unchanging cosmological constant. If it isn't, he added, there will be another Nobel Prize waiting for whoever nails down the details. Another researcher working on alternative dark energy theories, Celia Escamilla Rivera, offered a similarly candid observation about just how unsettled this area of physics currently is, noting simply that new theoretical proposals seem to arrive practically every week. It's worth appreciating just how differently each of these new instruments approaches the same underlying question, because that diversity of method is exactly what gives their combined results so much weight. DESI works by measuring redshifts directly, tracking the actual three-dimensional positions of millions of individual galaxies and quasars, and using the baryon acoustic oscillation standard ruler, described earlier, to gauge distances across cosmic history. The Vera C. Rubin Observatory, by contrast, will lean heavily on weak gravitational lensing, the same basic phenomenon that revealed dark matter's presence in the Bullet cluster, but applied here on a statistical, universe-wide scale, measuring the subtle, systematic distortion in the shapes of countless faint background galaxies as their light bends slightly on its way to Earth, passing through the accumulated gravity of everything in front of them, a technique researchers call cosmic shear. Euclid combines several approaches at once: precise galaxy shape measurements for lensing, alongside spectroscopic redshifts for tens of millions of individual galaxies, spread across a huge swath of the sky. And the Roman Space Telescope is being built specifically to conduct extremely wide, extremely deep supernova surveys, adding still more high-quality Type 1a data to the distance ladder method Perlmutter, Schmidt, and Rees pioneered back in the 1990s. If dark energy really is evolving over cosmic time, as DESI's own data increasingly suggests, that same signal should eventually show up independently in the weak lensing measurements coming from Rubin, in Euclid's combined spectroscopic and imaging survey, and in Roman's expanded supernova catalog. Multiple independent techniques converging on the same conclusion would be exactly the kind of evidence needed to move this question from an intriguing hint to something approaching a settled discovery, which is precisely why so many billions of dollars and euros have been committed to building instruments that, on the surface, all seem to be chasing slightly different pieces of the exact same puzzle. So where does all of this actually leave us? We have an expansion whose current rate we genuinely cannot pin down with confidence, because two rigorously tested, independently verified measurement techniques keep giving us two different answers, and we've now ruled out the easiest explanations for why that might be happening. We have a mysterious force, dark energy, making up more than 2/3 of everything that exists, driving that expansion to accelerate, sitting alongside an equally mysterious form of matter, dark matter, making up more than 1/4 of everything else, first glimpsed by Fritz Zwicky in the 1930s and dragged into the scientific mainstream by Vera Rubin 4 decades later. We're now facing fresh evidence suggesting even the basic behavior of dark energy over cosmic time might be more complicated than the standard model assumed for the past quarter century, and an entire new generation of billion-dollar telescopes has been built specifically to find out. And we have a universe that is, this very moment, permanently erasing our future access to more and more of itself, year after year, as galaxies slip past a horizon we can calculate but never cross. Before moving into what all of this might mean for the universe's ultimate future, it's worth laying these three separate mysteries side by side, because taken together, they say something larger than any one of them says on its own. The first mystery is dark matter, something making up roughly 27% of the universe, first suspected by Zwicky in 1933, effectively confirmed by Rubin's rotation curves in the 1970s, and directly imaged, in a sense, through the bullet cluster's separated mass in 2006, yet still, more than 90 years after Zwicky's original observation, of completely unknown physical composition. The second mystery is dark energy, something making up roughly 68% of the universe, discovered essentially by accident in 1998 by two teams expecting to find the opposite result, tangled up with a vacuum energy prediction from quantum physics that turns out to be wrong by about 120 orders of magnitude, one of the largest and least explained discrepancies in the whole of science. The third mystery is the Hubble tension itself, a disagreement over the universe's current expansion rate that has only sharpened, rather than resolved, as measurement precision has improved, standing today as arguably the most actively contested open question in cosmology. Stack these three mysteries on top of each other, and a genuinely humbling picture emerges. Ordinary matter, the stuff of stars, planets, and everyone who has ever lived, accounts for less than 5% of everything that exists. The remaining 95% is either something we cannot directly detect, something whose basic behavior over cosmic time may not match our leading theoretical model, or something whose present-day rate of change we cannot even measure consistently using our two best available techniques. Modern cosmology, for all its genuine successes, from Big Bang nucleosynthesis to the cosmic microwave background to a century of increasingly precise expansion measurements, is still built on a foundation where the majority of its subject matter remains, by its own admission, not fully understood. If the universe's ultimate expansion behavior stays roughly as it is now, cosmologists broadly expect one of a handful of possible long-term outcomes. The most widely favored scenario, based on the balance of current evidence, is something called heat death, sometimes called the Big Freeze or the Big Chill, in which the universe simply keeps expanding forever, growing steadily colder and more diffuse, until eventually there's no usable energy gradient left anywhere to do any kind of work at all. No burning stars, no chemical reactions, nothing but a maximally spread out, maximally cold, unchanging universe. Under current models, stars are expected to keep forming for somewhere between 1 trillion and 100 trillion years before that process finally winds down completely, and full heat death itself is projected on a timescale so vast, somewhere around 10 to the 100th power years, that the number stops meaning anything intuitive at all. It's simply larger than almost anything else we ever try to measure. The path toward that eventual heat death, according to researchers who have worked through the physics in detail, unfolds in distinct, almost unbelievably long stages. Once star formation finally winds down, whatever remains, dead white dwarfs, neutron stars, and black holes, is expected to persist for an enormous stretch of time afterward, with black holes eventually becoming the dominant objects left in the universe, simply because everything else fades away faster. Even black holes are not expected to last forever, though. According to theoretical work building on Stephen Hawking's prediction that black holes slowly radiate away mass over time, even the most massive black holes are eventually expected to evaporate entirely, leaving behind close to nothing at all. And then, according to some of the more speculative but scientifically grounded proposals about what might happen after that, on timescales so long they're written as 10 raised to the power of 10 raised to another large power, calculations suggest that the near-total emptiness left behind could still, purely by extraordinarily rare random quantum fluctuation, occasionally produce a fleeting, momentary conscious observer out of otherwise empty space, sometimes called a Boltzmann brain in the physics literature, before promptly dissolving back into nothingness. It's a genuinely strange note to end a story about the fate of the universe on, and it's worth being honest that this final stage sits at the very speculative edge of theoretical physics, rather than among its well-established predictions. But it's a real and seriously discussed possibility in the scientific literature on the universe's ultimate long-term fate. One small example of just how strange and unresolved even our best current physics becomes once you push the timescales far enough into the future. A more dramatic, though currently less favored possibility is something researchers call the Big Rip. If dark energy's push against gravity keeps strengthening over time rather than staying constant or weakening, as the newest DESI hints suggest, it might actually be doing the opposite of, then at some point in the extremely distant future, that repulsive force could grow so overwhelming that it tears apart everything that's currently held together by gravity or any other force. Entire galaxy clusters first, then individual galaxies, then solar systems, then planets, and ultimately even atoms themselves, ripped apart by the sheer runaway acceleration of space. Current data doesn't rule this scenario out entirely, but it does push it, if it happens at all, extremely far into the future. A third option, a big crunch, in which the expansion eventually reverses and the entire universe collapses back in on itself, is now considered unlikely given what we currently understand about dark energy's behavior, though it remains a mathematically possible outcome under certain theoretical conditions. And it's worth noting again that DESI's own hints about weakening dark energy, if they hold up, would actually make some version of a big crunch somewhat easier to imagine over extraordinarily long timescales than researchers might have assumed a few years ago. One more small example of how these different threads of evidence connect back to each other in ways that keep reshaping the overall picture. Long before any of those grand, cosmic-scale endings could ever play out, our own solar system has a much more immediate appointment on the calendar. In roughly 5 billion years, our own Milky Way galaxy is expected to collide and merge with its neighbor, the Andromeda Galaxy, currently sitting about 2.5 million light-years away and closing the distance at roughly 300 kilometers per second. This isn't merely a rough guess. Researchers concluded that the collision is essentially certain to happen after analyzing years of precise Hubble Space Telescope observations tracking Andromeda's actual sideways motion across the sky, not just its approach speed toward us, confirming that the two galaxies are on a genuine collision course rather than destined to simply pass by one another. When the merger finally happens, the two spiral galaxies will not so much shatter as slowly blend, their stars passing by one another across enormous, mostly empty distances, gradually settling over further billions of years into a single, larger galaxy, sometimes informally nicknamed by astronomers as a combination of the two original names. Our own solar system, along with whatever remains of Earth by that point, would most likely simply be flung into a new orbit within the resulting merged galaxy, rather than being destroyed outright in any direct stellar collision. Since the distances between individual stars, even within a colliding pair of galaxies, remain vast enough that direct impacts between stars are exceedingly unlikely. Around that same time, the Sun itself is expected to swell into a red giant, and within perhaps 2 billion years after that transformation begins, it's expected to consume the Earth entirely. Compared to the almost incomprehensible timescales involved in heat death or a potential Big Rip, 5 billion years sounds almost soon. What's remarkable, stepping back from all of this, is just how much of what we now take for granted about the universe, that it's expanding, that it began in an extraordinarily hot, dense state, roughly 13.8 billion years ago, that its expansion is accelerating rather than slowing, that the overwhelming majority of everything that exists is something we still cannot directly detect or fully explain, has all been established within roughly the last 100 years, and much of the most consequential of it within only the last 3 decades. Henrietta Leavitt spent years hunched over photographic plates at Harvard, cataloging thousands of variable stars by hand, and handed the entire field its first working ruler for measuring the universe, without ever getting to see what that ruler would eventually be used to discover. Georges Lemaitre worked out the theoretical foundation for cosmic expansion using nothing but pen, paper, and Einstein's equations in 1927, and had to wait years before the wider scientific community caught up to what he'd already figured out. Fritz Zwicky spotted evidence for dark matter in 1933 and was essentially ignored for nearly 40 years, until Vera Rubin's patient methodical study of galaxy rotation curves in the 1970s made it impossible to dismiss any longer. Penzias and Wilson stumbled into direct proof of the Big Bang almost completely by accident, while trying to eliminate what they assumed was interference in a communications antenna. Perlmutter, Schmidt, and Rees set out expecting to confirm that gravity was gradually slowing the universe down, and instead uncovered evidence for a mysterious accelerating force that nobody had previously theorized needed to exist at all. And right now, in 2025 and heading into 2026, an entirely new generation of instruments, including DESI's expanding dataset and the freshly commissioned cameras at the Vera Rubin Observatory, are suggesting that even our most basic assumption about dark energy, that its strength never changes, might itself need to be revised. There's something worth noticing in that list of names, beyond just the sequence of discoveries itself. So many of the people whose work turned out to matter most in this story worked for years without recognition, or received recognition only long after the fact, or in some cases, never received it at all. Vesto Slipher spent the better part of a decade patiently measuring redshifts that later became the entire velocity axis of Hubble's famous diagram, and his name barely appears in most popular retellings of the discovery of cosmic expansion. Henrietta Leavitt catalogued thousands of variable stars by hand, without ever operating a telescope herself, handed the field its first reliable cosmic ruler, and was nominated for a Nobel Prize 4 years after she had already died, by a mathematician who didn't yet know she was gone. Georges Lemaitre worked out the theoretical foundation for the expanding universe 2 full years before Hubble's observational confirmation made headlines, published it in a language and a journal almost nobody read, and had his own priority quietly written out of the story for nearly a century, before an international vote in 2018 finally restored his name to the law he helped establish. Fritz Zwicky spotted the first hard evidence for dark matter in 1933, and was largely dismissed as eccentric for describing it, his insight sitting unexploited for close to 40 years. Vera Rubin spent months confused by her own data before she and Kent Ford understood what they were looking at, then spent the rest of her career watching dark matter become one of the central pillars of cosmology, while she herself, by the account of much of the astronomical community, never received the Nobel recognition many believe her work warranted. None of these were failures of science. If anything, they're evidence of how science actually tends to work in practice, slowly, unevenly, dependent on who happens to read which obscure journal, who gets credited on which paper, and how long it takes the rest of a field to catch up to an idea that turns out, eventually, to have been correct all along. That's really the through line connecting a Harvard computer cataloging variable stars by hand in the 1900s, an astronomer in Arizona quietly measuring the velocities of smudges of light nobody yet understood, a Belgian priest in 1927 told by the most famous physicist alive that his physics was abominable, a Swiss astronomer coining a memorably blunt German phrase in 1933, 2 radio astronomers cleaning bird droppings out of an antenna in 1964, a woman confused by her own data on the Andromeda Galaxy's rotation in the late 1970s, 2 rival supernova hunting teams in the late 1990s who each expected to prove the opposite of what they found, and a modern instrument perched on a mountain in Arizona collecting data on 15 million galaxies today. Every single time cosmologists have felt confident they finally understood how the universe behaves, the universe has responded with a number that doesn't quite fit, a measurement that refuses to agree with the one taken a different way, a signal in the data suggesting the story isn't finished being written. The universe has been expanding for 13.8 billion years. It's been accelerating for roughly the last 9 billion of those years, and depending on which of the world's most careful measurements you trust, it's doing so today at somewhere between 67 and 73 kilometers per second for every megaparsec of distance. 95% of everything driving that expansion and holding its galaxies together is made of 2 substances, dark matter and dark energy, that nobody has ever directly detected and nobody can yet fully explain, and the small mathematical term Einstein once invented purely to keep the universe from moving at all has turned out to be, almost by accident, the closest thing physicists currently have to a description of the very force now tearing it apart at an accelerating rate Nobody currently alive knows which of the two competing Hubble constant measurements, if either, is actually correct. And depending on which team's instruments and methods eventually win out, or whether both turn out to be capturing something real that our current model simply doesn't account for, the answer could reshape our understanding of the universe's ultimate fate all over again, tipping the balance between a slow, cold heat death stretching out over 10 to the 100th power years, and a far more violent Big Rip that would eventually, if it happens at all, tear apart galaxies, stars, planets, and atoms themselves. For now, all we can say with real confidence is this: the universe is getting bigger. It's doing so faster than it used to. More and more of it is slipping permanently beyond our reach every single year that passes. And the exact speed at which all of that is happening, and where it's ultimately headed, remains, for the moment, one of the most genuinely unresolved questions in all of modern science.